and welcome back to, this will be the activity for week 2. I'm going to first kind of discuss what we'll be doing, what we're trying to aim at, and then I'll show you the equipment used to gather the data in this lab, and then I'll try to explain the kind of basics behind the statistics that you're going to be using to analyze the data. And then we'll go into a little discussion of what the data and the outputs actually look like. I'll probably leave you to do the 4 discussion questions at the end, but I want to show you where the information comes from and how it relates to what we were talking about earlier. So basically, what this activity aims to do is to assess if the body size, like height and mass, actually influences the biomechanical fitness constructs. So these constructs, and I call them constructs often when you're doing statistics, are things you can measure like strength and torque. And then that can also be translated to how much work output and how much power output an athlete can have. I mean, you've got a very long introduction from the lecture about how absolute body size is shown to be important, and it's becoming more and more specialized for different sports. And so look at chapter 3 and 4 for trying to get the background information, or if you've listened to the lecture, you've probably heard enough. So, but the chapters are much more in depth and give actual data, so definitely look at them. Okay, so basically what we have here is there are different methods to measure height and mass, and I'm going to show you those. Those are pretty basic ones. But then there's also some more sophisticated measures that allow you to get power, work, and force measurements that you weren't able to get in the past, and so that gives you actual biomechanical numbers that you can relate to a person, which is really quite nice. And that's collected here with a machine called the Wk2 norm, which I'm going to show you in a minute, just very briefly. And then you also want to get not just mass calculations. There's new like impedance measuring things that allow you to get the composition of your body, so how much fat per muscle, and even as much detail in how much is in each leg and each arm. And so I'm going to show you very briefly also the body composition analyzer BC418 and just explain briefly how it works. And then later I'll show you an output from both that Wk2 norm and this other body composition analyzer. So bear with me a little bit. I gotta flip the videos around and try to show you these things. So let me escape from here and come back up. So this contraption right here is called the Wk2 norm. And what is very interesting about this is where we're going to get our work, our power, and our torque measurements from. So if you wanted to measure an athlete, you would put them in this chair, you'd strap them in, make sure you were isolating the movement of the leg that you're wanting. So you got some different straps to do it. Somebody's going to show you the actual steps to do this when you're doing the intense activity, but I'm just going to briefly explain it so you know what we're talking about. So this machine would turn around, and attached to it you got different measurement devices. So you got this here, which you would put your leg on, and you'd have the athlete pull down or push up as fast as they can, and this will measure how fast it's rotating and how much force the athlete can push against it. And by knowing that speed and the force that the athlete uses, you can actually calculate how much work, how much power, and of course how much torque it can generate by pushing that. And so that's what we're going to use here. Is some people have been put in this nice contraption, this Wk2 norm, and they've done, I believe, a leg curl, and you can see how much power they're able to generate. So that's the data you're going to see as far as the biomechanical factors. Also, 6 participants had their height measured here. And so you just stand here with your heels against there and somebody measures your height, quite basic. Now, the other one second, I gotta switch cameras, is the body composition analyzer, BC418. So it's zooming in there, and you're going to get quite a nice view. But right here, you would have this is the body composition analyzer. And what you get are 2 handles. One that you hold in your left hand, one that you have in your right hand. They have metal on them to allow the impedance measurements to go through. So skin has to actually touch that metal. So you would stand, and you'd have them take off their shoes and socks so they stand on the feet, because you can also see that the feet also have metal. And so you stand there with these in each hand and your feet on the sensors. And it takes impedance measures, and it measures how much your fat range is, how much muscle you have, and it does it so specifically that you know it in your legs for each individual leg and each arm, because you have an individual sensor on each of those. Okay, so those are the measurements we're going to be working with today. So you have your biomechanical from your HUMAC norm, you got your height from the stadiometer, you got your muscle and fat content from this body composition analyzer, and then you also get a basic scale to measure your mass. And so those are some of the basic factors we're going to look at. So now that we know approximately what we're going to look at, I'm going to show you a little bit of basic statistics, because whenever you have different variables, and variables is just a different term for something you measure. So height would be a variable. Weight is a variable. And if you want to see how those relate to each other, you do some basic things. So the data you have there has been collected from 6 different people. And so in statistics, there are, I think, 3 main things that you can remember. So one is what N stands for, and one is the P, and the other is R. And you can get a lot of different stats and a lot of different things in your mind, but these are the most important things that people will, the N, the P, and the R. So you get N is your sample size. So in this data that is in your worksheet, you have 6 different people with the data filled in. So since there were 6 different people, for this, the answer is 6. So there, how many samples you're going to analyze per study you do. The second is P. P-value can mean many different things, but the main thing it is it tells you if it is statistically significant or not. So if you know if it's statistically significant, you can set, and they always talk about statistics has such a unique language that you have to know how to interpret their lingo to get anything from it. But basically, they set a level, and they call it a level, to 0.05. This can be changed to anything you want, but this is the standard. What this means is that if 5% of the time, if you wouldn't find that relationship just by chance in 5% of the cases, then it's statistically significant. So if it's telling you that this change has to be related to the other one. It is related, and it just didn't happen by chance. And it could have only happened by chance 5% of the time. So it doesn't have to be related, but there's only there's a less than 5% chance that that is related by chance. So that's what your p-value tells you. It tells you what percent of the time that could only happen by chance. And so then your R value. And your R value tells you how much of, it's often what you call a correlation coefficient. But it really tells you how much variance is explained. So it tells you explained variance. Now I'm going to show you a bit more what I mean by explained variance. But if you can remember that n is the sample size, p is the statistical significance, which means what is the percent that it would happen just by chance, and R is the explained variance. Those are the three main things that you need to remember about stats. And if you can remember those in this class, that'll really help you understand the different discussions you'll have by how the biomechanical factors relate to one another. Okay, so to explain a bit more, because one of the basic things you do when you analyze data is a correlation. So you take, so what they've been doing often is height, how tall you are, and the mass, how much you weigh. And you measure that on different people. So our sample size here is 6. So, this person has low height and low weight, and this is high height and high weight. And this is just plotting each individual person. Each dot represent one subject, one person who was measured. So, if this was me, this is my specific mass with my height, 180. You don't really need to know that, so you get a specific weight there. And basically, a correlation is to try to define if there is a relationship between those. So normally, you'll see a line that goes through the data. And this line here, this, if you ever had the basic mx plus b, this definition of this line is the relationship between height and mass. So you can take two variables and have one relationship. And this is determined basically by reducing what they call residuals. So residuals are, okay, so you got this data point, and you got this distance between each data point to the line, okay? And so these distances here are what they call the residuals. And basically, they're making a line that goes through the points as much as possible to where that distance, if you sum up all of these distances to that line, it's as small as possible. And the reason you want to do that is because you want to make this relationship explain the data as best as possible. So if you have a line that goes like this through the data, you're going to have really big residuals. And that means it won't explain it very well. So you really want to try to make the relationship explain the differences. And so saying that, that's why that R value, it tells you how low this is. So how small your sums of your residuals are. The lower these distances are to that line, the closer the data matches. So let me give you a quick example of well matching data and not match. So if you got data just spread all over and you got a line through there, you're going to have a bunch of residual. Now you can have some relationships where it really is very clear, and so you're going to have very limited residuals. And so this value here, this R would be really high. And here, the explained variance would be very low. And this is explained variance because that residual is saying how much change it is from each one. So each residual tells you how much variance there is. So since these residuals are very tiny, you get a very high R. It's saying this line really, it explains that data really well. Whereas here you got a bunch of other things that are happening. So this R will be really low. So R goes on a scale from -1 to +1, right? And so if you get, so basically the positive tells you if the slope is positive. So here it's called a positive correlation, and your R would be positive, and it would be between 0 and 1. That's a decent one. It'd probably be about a 0.7 or something. It'd be closer to 1 than to 0 because it's a pretty good correlation. The residuals are there, but they're not too strong. Now, if you had a negative R, so this would be about 0.7 or so. So if you had a negative R, where you got a variable here, and you got different data points, and the line that would best fit it would go like this, then you would have like an R equals -0.7. So it's always between -1 and 1, and the how close it is to 1 tells you how much of this variance that is explained. So R tells you explained variance. N tells you how many samples they measured. And P value tells you whether it's significant or not. And P is very important. So if you have a relationship, like I showed you before, where you have a bunch of numbers that are just extremely spread, and you have a data point through there, and then you have a number that's quite close. So you're gonna, on this one, the difference is gonna be, you're gonna get a p-value that is really high, equals about like maybe 0.8 or something, 80, and you're gonna get an R value that is really, really low. So it's slightly upwards, so I would say 0.05. And if you have a good relationship, you want a very low P and a very high R. And so here, you'd probably get quite a high or a low P, so like 0.01. And as long as that is, so this is then less than the 0.05. And that's important, because if it's less than that 5% threshold, then it's significant. And so this would be significant. You say, hey, look, the variable 1 and variable 2, they make a relationship. And then this R value, if it's equal to 0.7, that means that, oh, it's significant. That doesn't normally happen by chance. And the R value tells you how much of that variance is explained. And the more of it that's explained, the better the relationship, the better this equation will tell you how it does. And this is the basics behind a correlation. And so these are the things you need to consider when you're looking at the data and trying to figure out which relationships it is. So basically, you want to look at N, because sample size is extremely important. If you only have 5 people doing it and you're trying to do relationships, you're not going to be able to tell if it makes a difference or not most of the time. You'll get relationships that happen or don't, but it's kind of by chance because you don't have enough people to really see the variance in the population. But if you have like 1,000 people and you don't see a relationship, you can probably you have more power behind those stats to be able to say, yes, this relationships exist. So if n is low, that's not good. It's not good. It means that your data can't explain too much. You want a decent n. And I mean, there's always arguments on there, what is decent and what is big. It depends on how many there's so many things it depends on, but absolutely less than 10 is too small. Less than 50 is probably, around 50 is maybe okay for some things, but the more and more factors and things you build in, you need thousands and thousands of data points sometimes in order to tell. So a low n is not good, is one thing to remember. So p-value, typically less than if you get less than 0.05, that means it's significant. And you want a low p. So you want a high n, a low p, and a high r in order for you to have a good correlation. So the higher the r, the more variance as explained, it means the relationship is stronger and it matches, like one variable increasing, the other one does too, or vice versa. So that would be the basics behind the correlation. The other basic stats we'll look at are your basic average and standard deviation. So they call these descriptive statistics. And I'll probably talk to you a bit more about that over when we look at the data, which I'm going to go do now. So 1 second, I got to switch the cameras. Okay, so now what we want to look at is a bit more of what information we actually got out. So I showed you earlier that machine, the HUMAC norm, which you would have the athletes sit in, and this measures your torque and your power and your work. This here is showing you an output of what information you get from that machine. So basically, what you see here on your left is torque, and you get the angle that it goes through. So as the athlete is pushing against it, you can see the torque increases as he's rotating, or she, and it reaches a peak and then comes back down. And so this peak torque will be analyzed. And then you can do it on your right leg and your left leg and see how it differs. And from that torque in this graph, you're also able to calculate the rotational work done. And work would then be this torque value and multiply it by the angle that it travels, because that's measuring both the power, the torque, and the rotation. And multiplying those together will give you your rotational work. And then to get to power, you would take the torque value, and also multiply it by angular velocity. So angular velocity would be how, like, the quickness that this angle goes with time. So it'd be the slope of the angle curve. Angle versus time, not torque. So if you plotted angle on the y-axis and time on this, you get a different curve. And how that angle went up with time is how you would get your angular velocity. And so if you multiply the torque value you get times your angular velocity, you'll get the power. And so power is, again, torque times angular velocity. Work is torque times the angle, so the distance traveled. Okay, and so that's how you get the basic biomechanical parameters out of the HUMAC norm. It also gives you some time and delay seconds, which might be interesting for different tests, but not in what we've done today. So this next output is what you get from that machine that analyzed the body composition. So basically this subject here, 22 years old, male, he has 16 kilograms of fat mass and 77 kilograms of fat-free mass, and his body fat percentage, 17.1, it fits right in the normal range. His BMI analysis falls a bit high in the overweight range. He's 189 centimeters. His body water analysis is in a good value, 60.7%. You can look at individually how much fat is in each portion of his body. You can look at the muscle mass in the different areas. You get the body mass distribution, whether it's in muscle or fat mass. You also are able to see in each of the arms and legs just the percentage of fat, how much fat-free mass, and then it takes that information and it gives you a predicted muscle mass. So this is all done by calculations based off of electrical impedance, so some of it can vary a little bit, but you get some good information to work on and a good baseline for athletes to get them to work towards improving. Okay, so that is how the data was collected, what you get when you get out of it, and now I've talked a little bit about the statistics that go into analyzing the correlation coefficients. And so we want to then look into a bit more detail into how this information looks. So we would go into a program, and here's the data that's been collected. You have 6 different participants ranging from about 1.6 meters to 1.91, and you can see the different mass. Basically, anytime you first look at a data set, you want to get what they call the descriptive statistics. And these descriptive statistics allow you to see what the average is and the standard deviation and how many samples there were. As you can see in this example, every person had everything measured because n equals 6 in all categories, so that's easy. Then you can look at the averages and just get a feeling for how tall, how big your sample size is, and get a little bit of an overview of how much force they were able to produce. So here is the force values. So you get the torque, the work, and the power variables. But then they also so these are what you call absolute values. These are values that were directly measured and haven't been altered by math or anything. Now, the relative peak torque and these are relative torque, relative work, and relative power. Basically, what was done in order to make the variables more consistent across the population, you can try to remove the influence of another variable by dividing by it. So what they did was they took the peak torque and divided it by the mass of each individual patient, and they output this relative peak torque. And so in this way, it was trying to get a sense of what the torque would be without mass being a factor. And so you could do it and divide it by height in order to try to get height out of there. But this one was done by dividing by the weight of a person. And so that way it's called relative because you remove a variable and it wasn't directly measured, whereas it gives you a better comparison between subjects that are, especially if they have a large variation in that, in the mass in this case. And then the absolute are just the actual values measured. And then you get this what FFM, it's actually stands for fat-free mass. So the amount of your body composition that is free from fat. Then you also have your muscle mass in weight and your adipose mass. It's quite interesting if you add the adipose mass and the free fat mass, it gets quite close to the total body weight, but it varies a little bit. So there must be something in the calculation of the program that isn't fully the same. So like if you come here, so this guy's 90.5. If you look up their fat-free mass, 77.3, and their adipose mass, you would get 90.9, and it's 90.5. So it's close, but there's something a little bit funny there. But these values, the fat-free mass, the muscle mass, the amount of fat you have, the left muscle and right muscle, these give you just factors based off of the body composition. These are your basic height parameters. These are your absolute biomechanic parameters, and these are your relative ones. So those are your basic data you're working with. You can see what the average of the 6 people were, and then standard deviation is very important, because if you have a large deviation, especially here, see about 13 kilograms between the people, this will make the data not be able to be, like it detracts from the ability to find statistical significance. To see, you would need a bigger population to see how this fits. If you have large standard deviations and low population numbers, you're going to not be able to tell much from the statistics. Also here, you get quite large variances in work. This is about, a fourth of the data, so it's about 20%, 20 to 25% of that actual value. So it's quite large standard deviations, and if you have that, it makes it very hard to be able to understand what's happening. So one of the first parts of the assignment was to be able to interpret the correlation matrix that has been derived. So I'm going to look at it with you real quick to try to, or just to talk you through what's being looked at, and then the second point is, were there any significant correlations between height, mass, and the biomechanical constructs? And so we want to kind of look and see if these exist. So we go to the correlation matrix. So basically, okay, so here's a correlation matrix. What you see here is you get your variables. So here you get height, your mass, your peak torque, your work, and you get all of these variables across the top. And you also get the exact same variables in the same order down the side. So all of if you looked at that table, again, the basic table, these are the same variables, and you got them across the top and down the side. And so when you take one variable and have the same one, if you plot them against each other, they will be the exact same. And because they're the exact same, their R value will be an exact 1. And so they perfectly correlate. And so whenever you see a correlation matrix, when you go down the diagonal, it'll always be 1 here. So your height with your height is 1, and you'll get the sample size that you have. And so for mass, you'll get 1. Mass and mass, you get 1. and then peak torque and peak torque, you get 1. So all down the diagonal, you'll get a 1. But to then interpret more fully how the height and the mass correlate, so you go down your column and then across your row. And so here, you get an R, this Pearson correlation, that's actually the R value I was speaking of earlier. And it'll be reported as R everywhere. And so this tells you how much variance is explained. And if you see this value, the 0.867, that's a very high correlation. And then you see the significance here. That tells you that that relationship not only explains a lot, it will happen by chance less than 5%. This actually says it could happen by chance 2.5% of the time. And so this is how you interpret the correlation matrix. And then you just go through, and let's look at height first. So height and mass, they're correlated, but then you look at the torque, that's not significant, so it's not less than that 0.05. And so in the R value, see how it's decreased from there? That doesn't show a good relationship. And then you kind of work down and you look at height and work, you don't really see you don't see a relationship there. You look at power, there's no significance. The value is very low. Again, here the significance is low. You can't find any relationship to any of those biomechanical constructs. So you got peak torque to power to relative work, and you just don't see any significance. And then you go and look at the fat-free mass, muscle mass, adipose, so the fat mass in the left and right muscles. And again, there are no significant correlations. And so what you can say from there is that height is related to mass. There's significant, if mass increases, so will height. And you know that as height increases, mass increases because this relationship is positive. There's no negative sign there. Like if you see here, since there's a negative, it means that if one's increasing, the other's decreasing. But if it's positive, as height increases, your mass is also expected to increase. But now if you pick mass as the column you want to go down, you go down and you see that yes, it's related to height, but to no other factor is it significant. And so then you continue to do this process for each variable. You then look at peak torque, right? It's not significant to both height or mass, which we've already seen from before. But what you do start to see is that it is related to both work and power, both things that are calculated from the torque parameter. So it makes a bit of sense that these are all related because they all have torque in the equation. Then you look at relative torque, relative work, and relative power. I believe that this typically should be related to each other, except our sample size is too small. But that's just my speculation. But the relative and the absolute do not correlate in this instance. And so you can't see any relationships. And then if you try to look at body composition parameters, for all three of these, you do not see any significance between the correlations. So you can't see any relationships between the variables. And so then if you move over to the relative work, again, you find very similar things. There's no relationships between the height or the mass, the absolute peak work torque. But then within the relative, within the other relative measures, you do find significance. So relative peak torque is related to relative work and relative power. And this is high significance, 0.95, that's extremely high, and 0.875. So they're related to each other, but not to the absolute. But the one interesting relationship I've seen here is the peak torque value, the relative peak torque. So when it's been made relative based off of the mass. So you take your torque and you divide by your mass of your body, you get that this fat-free mass is related to torque. And so there is a relationship there. Actually, I am misspeaking. This is just kind of, that's the R value. See, that's the Pearson correlation. And this is the significance. So it's extremely not significant. So that just gets what you do whenever you do highlight cell rules just based off of basing. So there's no significance here because this p-value, the significance, is not less than 0.05. It's actually very low relationship, about as low as you can get. And so only relative torque, relative work, and relative power are related. All the others are, and then the peak torque, the work, and the power, the absolute measures, they're all related to each other. And then height and mass are related to each other. And then if we go down here and we look at your fat-free mass to see if it relates to all your body composition ones, you can see there is no relationship to height or to mass, because these p-values are all more than 0.05, and the mass values are all bigger than 0.05. But if you do look closely at the fat-free mass, the muscle mass, the left muscle, and the right muscle, these values here, they're getting quite close to significance. See how they're between 0.5 and 0.1? People then will start to talk about trends. And so it does look like the mass is probably, it's not significant right now, but it might be related. But you have to remember these 6 participants are not enough to get a really good idea of the actual situation. So you'd want to get more participants. If you wanted to do a better study, you'd get more participants and see if these relationships would develop a bit more. And you probably would start seeing that mass is related to your fat and your fat-free mass and your muscles. So this currently isn't related, but it might turn out to be a relationship later. And then here, this is extremely close to being significant, both of these. So if you look at peak torque and the fat-free mass and the muscle mass, you can kind of see a relationship. If you have more muscle and less fat, you're likely to get a good relationship. What is interesting here is that it's not quite significant, but again, the significance has to do with the low sample size. But you can see these trends happening. This p-value is very close to 0.05. You get a very high R value, and when I say very high, typically over 0.8 is considered very high. And so you're kind of seeing that the power is quite highly related to your muscle mass, and that 0.8 explains a lot of the variance. Whereas if you look at the fat mass, you don't get as much significance. You get 0.5 rather than 0.05. And the relationship, you don't get as much variance explained. So it's not as good of a relationship. And on top of that, see how there's a negative sign there? If the trend, even though it's not significant, is saying that if you have more fat, you're going to have less torque. And so the fact that this is negative, and having more fat makes torque negative, work negative, and power negative, does show you that having fat might hinder it. But the problem is right now you don't have any significance. So you really want to go get more participants and see if that might be a real relationship later. And you can then look here and see that your muscle mass is quite substantially, almost significant, even with 6 participants, nearly significantly related to how much torque, how much work, and how much power. And these are all positive. So if you increase muscle, you're going to increase your torque, your work, and your power output. You can see for the individual muscles kind of similar trends, but it's not. They're less, like further away from significance than the fat-free mass and the muscle mass. So quite interesting that it's getting quite close to being significant. Then if you look at the relative ones, and you really don't see much. If you kind of try to take out how much someone weighs, it really doesn't help you try to see if there's a relationship between those. But what you do see is that your muscle mass, your fat-free mass, your muscle mass, they're related to each other. So muscle mass, fat-free mass, it's not highlighted because it's 0, and so are these. These are just like perfect relationships. If your fat-free mass to muscle mass, these are almost 1-in-1. So basically, if you just chose one of them that explained the most, you wouldn't have to analyze all those values and then do your fat mass. So this is quite interesting in that you definitely do get the major trend of the height and the mass being heavily related. You see that. You also see that the biomechanical parameters are fully related, that if you increase torque, you're going to increase work and power. And the same thing for the relative work, torque, and power. Those all relate to each other in this region. But what gets kind of interesting over here, even though you can't see it significantly yet, is how the mass relates to the fat-free mass, the muscle mass, and the fat mass. So you can see that there's a positive relationship. The more muscle you have, the more torque, the more work, and the more power you're going to get. Whereas if you get adipose, even though this is not significant, you get negative relationships. So that's quite interesting. So you want to decrease your fat. That matches what's been said in the lecture, and to help improve performance. Though that's not significant, it still shows that like general relation. It also shows that your fat-free mass and muscle mass, if you increase your muscle, you're going to increase your power output. So that matches. It also matches that if you increase height, you increase mass. So those relationships were found, that always stated in the book. They're kind of found here. The big exclamation point is you don't have enough sample size to be able to make all of these determinations. So if you increase that, you're probably going to see a lot of these relationships appear. The fact that they start to with only 6 people is it shows that it's really likely a very strong trend, and also the fact that this Pearson, this R, the explained variance, is so high on these, that means it explains a lot of what's happening. So that would be the overview of how to look at a correlation matrix and interpret it. So from that, I'd quite like you guys to look at the discussion questions, try to take notes, and answer those 4 discussion questions. But hopefully this explained a lot. If you have some questions, hope maybe you can send me an email, or if there's a discussion board, get on there and discuss. That's a bit better. Then everyone can be a part. Hope this was good information, and see you next time.